So as Håkan said, this is a purely numerical talk, following up on the talk that Oliver just gave, and sort of pushing those results forward. So I think the long-term goals of this work are in part, of course, to inform potential future rigorous investigations. But those are probably down the line. What I'm going to talk about today is definitely work in progress, but I hope that it will be of interest to the people in this workshop. So this is joint work with Håkan and Oliver. Let's see, how do I advance the slide? There we go. So let's get into what I want to talk about. So the subject for today is what I'm deeming the binding energy maximum hypothesis, following terminology I think introduced by Gerhard Rhein and collaborators. So this basically states that the first critical value in a binding energy curve as a function of a parameter such as the central redshift coincides at least with the onset of instability. And so this picture that I have on the left, can you see my cursor in the screen? Is this?
Yes, I can see that.
You can see my cursor, okay.
Yeah.
So this picture encapsulates the idea, is that, so one considers sort of a family of steady state solutions to the Einstein Vlasov system, such as those referred to in Mahir's talk on Monday. And as Mahir said, you can parameterize these by, for example, the central redshift. And for each member in this family, one can associate this quantity, the binding energy. So this, as Oliver just mentioned, this is essentially the difference between the rest mass of the particles and the total mass of the gravitationally bound body. So if this is negative, or if this is positive rather, then it's energetically favorable in some sense for the mass to the body, the particles to be bound in a body. So the idea of this binding energy maximum hypothesis is that is basically, as you move along this curve of parameterized steady states, everything to the left of this extrema is stable, and everything to the right of this extrema is unstable. So this is widely attributed to Zeldovich and Novikov, the origin of this idea. As I understand it, from Ipser's paper in 1969, this was first sort of communicated privately to Kip Thorne from Zeldovich. Although most of the work in this steady states and in spherical symmetry has been done by Ipser, Fackerel, and collaborators. So Ipser in particular has sort of a series of papers on this subject, and in the first paper with Thorne, they give an argument that this binding energy maximum hypothesis must be false, and by paper 3, they are arguing for its truth. So this plot is taken from Ipser's, what I'm calling paper 3 in 1969. So this is the idea. There's been a number of numerical works in support of this idea. So maybe the first numerical work is probably this work of Ipser, but this was followed up by Shapiro and Tucholsky in 1985. So they give support that this hypothesis holds for a number of isotropic spherically symmetric models. And Andreasen and Rhine continued that investigation, so they show that also they give support numerically that this also holds for non-isotropic spherically symmetric models. So this is where I haven't introduced any terminology yet, but the microscopic equation of state would depend on the total angular momentum of the particles as well. The most thorough, I think, investigation of this hypothesis, as well as other related issues, is the recent work by Günther et al., also working with Gerhard. So they numerically investigate the evolution of steady states and perturbations thereof with a very high accuracy code that's distributed with a distributed parallelism. So I think in addition to sort of verifying this binding energy maximum hypothesis, I think this is the first observation that the instability is really, for these Einstein Vlasov system, is really associated with this critical point in the binding energy and not the critical point in the mass as a function of a parameter. So this so-called turning point principle. So this is very nice work. So they investigate a number of different steady state models, and in addition in multiple coordinate systems. So Gerhard might have talked about this morning, and while I was still eating breakfast. Let's see. As far as analytical results, it's much less is sort of rigorously known. If I can just coarsely summarize the status of or my knowledge of the status is that if one has sort of this sequence of steady states parameterized by, say, the central redshift, and each of these is an isotropic steady state. So this distribution function depends only on the particle energy. This microscopic equation of state is supposed to have a decreasing function of the energy, possibly with additional technical properties. Then on the one hand, if this central redshift is very small, then Mahir and Gerhard have shown that the solutions are linearly stable. This is essentially the Newtonian limit. Of course, as Mahir mentioned on Monday, it's not clear what this means for the nonlinear stability. On the other hand, if the central redshift is sufficiently large, then they have that the steady states are linearly unstable. So that's recent work with Lin. So there's a whole lot to be proved about the region in the middle analytically. So the question that I am investigating and presenting preliminary results on today is what happens if one extends this to the axisymmetric setting. So all the sort of motivation I just talked about was in the spherically symmetric setting, and also where the binding energy maximum hypothesis was restricted, or should be restricted, to spherically symmetric perturbations. So let's see. So I gave some motivation initially. For the remainder of the talk, I want to give you an idea about how we construct these steady states of the axisymmetric Einstein Vlasov system. And then what we do is we basically use these steady states as initial data in the code that was just presented by Oliver, and we launch with explicit or implicit, explicit perturbations or perturbations just introduced by the numerical discretization. And so we launch these initial data, and we watch the evolution. So I'll give you some sort of preliminary results on what happens with this binding energy maximum hypothesis, and some looking at the explicit perturbations. So let's see. Oliver just presented this 2 + 1 + 1 formulation. So I just remind you of the variables that appear in my talk in this single slide. So in this formulation, one reduces the Einstein equations to quantities which live on this quotient space of orbits of the spatial killing vector field. And on this 2 + 1 quotient space, one performs an ADM decomposition of the metric. So you have the metric tensor with a lapse alpha. We have this quasi-isotropic gauge, and so you have some fields psi and s are the dynamical fields. The length of the killing vector lives on this spacetime, and then one has these twist quantities, which are decomposed into the electric and magnetic parts. So this is just a reminder of the sort of fundamental fields that will show up, and I will, in the next slide, introduce an additional killing vector field so that we have the stationary equations. So for the stationary spacetimes, we of course have an additional time-like killing vector field. So if we look, this drastically simplifies the ginormous system of equations that was introduced in Oliver's talk. So in particular, these rescaled components of the extrinsic curvature that Oliver introduced, U tilde, W tilde, and X tilde are all vanish. The shift components can also be taken to vanish. And these components of the twist simplify. The magnetic part is 0, and the electric part can be written as this gradient of a twist potential, which I'm calling pi here. So for the stationary equations, the fundamental fields are this alpha, psi, s, and pi. And these fields only depend on r and z, the so-called meridional plane coordinates. So you can form a system of equations for these fields by introducing those simplifications into the equations that were in Oliver's talk. You can then further, you can obtain nice structure for these equations by introducing a special set of variables. So we introduced this alpha tilde variable, which is a renormalized alpha, and an s tilde variable. And this allows us to construct this partially decoupled hierarchy of equations. So the aspect that I want to point out in what we obtain here is you get a fully decoupled equation for this alpha tilde variable, followed by a system of equations for psi and pi, which are coupled and also coupled to the alpha tilde. And finally, you get an S equation for the S. So these are all elliptic equations. for each of these variables, and each one has an associated source term, which I've written in capital S. That depends on the Vlasov distribution function. So that's not enough to solve the system of equations as it is. So we still have the Vlasov equation. To close the system, we do the standard or somewhat standard trick in this business, which is to make an ansatz that the distribution depends on the spatial and momentum coordinates only through the conserved particle energy and particle angular momentum. So A here is an amplitude that is fixed in the numerical method, and this phi is a sort of a microscopic equation of state for how this energy and angular momentum dependence. Right. So for the 2 + 1 + 1 formulation of the equations, the energy and angular momentum can be written in some as these expressions. These V's are the frame variables that were introduced in Oliver's talk. So these rescaled momentum coordinates. So once one makes an ansatz of this form, the system that was on the previous slide then can be written as this nonlinear coupled integral differential set of equations for these 4 metric fields, which are solved with asymptotically flat boundary conditions. So the essential point here is that these S source terms can be written as they're written. They start out as integrals of F tilde against the momentum frame variables, and all of the. So when you write F in terms of the energy and particle angular momentum, you get expressions that depend only on the metric fields. So these are just integrals that you can do with some metric field dependence, and that enables you to close this system of equations. Let's see what I wanted to say next. Right. So to solve this system, the basic idea is that one makes some initialization for these metric fields and prescribes a total mass of the desired solution, and then you do an iteration, a fixed point iteration scheme. So the fixed point iteration consists of 2 steps. One is an update of the source term integrals, where you compute these S sources, and then rescale by changing that amplitude A, so that the total mass associated to these sources is whatever the prescribed mass is. So we always prescribe a unit mass in our code. And the second step is an update of the fields, which you can solve that system of equations in the natural way, given their hierarchy. So you solve for the alpha, then the coupled system for psi and pi, and then for S. And once those fields are known, you of course reconstruct the field alpha and the field S from their tilde counterparts. So this iteration is broken if once some prescribed tolerance has been reached for a residual of the equations. I want to mention that typically for forms sequences of solutions by using a path following approach, so that the initialization, as to initialize the fields for the solution of one, how do I say this? So to find a subsequent sequence solution in a sequence of solutions, one uses the previous solution as an initial guess. So let's say something more specific about this ansatz that we're using. So the specific ansatz that we are using in what I'm talking about today, that has been used in previous work with Håkan, is sort of this form. So this is a generalized polytropic type ansatz. There are a number of parameters. So this plus notation means that the argument is taken if the argument is positive, and it's zero otherwise. Such a combination might be raised to some power, k, for the energy part, and L for the angular momentum part. These parameters that show up in the arguments here, E naught, correspond to the maximum particle energy then, and this L naught corresponding to the minimum particle angular momentum. And I've also introduced this quantity chi, which I call the counter rotating fraction. So this is the fraction of particles which are rotating in the opposite direction as, say, the bulk. So you can have, in such configurations, you may, by setting chi equal to 0, have all of the particles rotating with the same orientation, and by choosing a different chi, you have some fraction of particles rotating in the opposite direction. So a common choices are chi equals 0 for all particles rotating in one direction, and chi 1/2, such that you have equal numbers of particles in each orientation, and in this case the total spacetime has 0 net angular momentum. Right. So such families of steady states have been constructed using an ansatz of this form. So, for example, in work with Håkan and Anders Log at Chalmers University, we have constructed these families of steady states. Each family might be parameterized by this minimum particle angular momentum. And the parameter that we vary in constructing these states is this E naught, which turns out to be in 1-to-1 correspondence with the redshift. So as you decrease E naught, this is sort of ends up decreasing the support of the solution and increasing the redshift, or the corresponding relativisticness of the solutions. So I'm plotting here sort of a binding energy type curve where one moves from low redshift, more Newtonian-like states to more relativistic states, and the binding energy is increasing, and at some point passes a peak. If you restrict to particles being sufficiently having sufficiently large angular momentum, you can avoid going over this peak altogether, and your sequences sort of take a different path. So these solutions that are constructed with this specific choice of parameters here, k and L being 0, have toroidal cross sections. There's a few snapshots of the energy density on the right-hand side here. this, I don't have the exact values, but this is decreasing the E naught parameter as you go down the page. And what we have found is if you decrease this in a rotating space-time, so chi equals 0, for example, where all the particles have the same orientation, you can decrease this E naught parameter sufficiently far, somewhere about 0.66, you observe ergo regions. So this is a region in space-time in which the time-like killing vector field turns over and becomes space-like, forcing all observers, all time-like observers at least, to rotate with the space-time. So what I'm plotting here is the energy density and a cutaway of the boundary of this ergo region in white. So as this ergo region initially forms inside the body, and then as one goes to more relativistic bodies, it extends out and to encapsulate the energy density. So there's some interesting sort of properties associated with these steady states. One question that we would really like to answer, but which I have nothing to say about today, is whether such states as these with ergo regions are potentially stable, or whether there are stable configurations with ergo regions. So there have been recent examples in the literature for fluid spacetimes which contain ergo regions and are stable on dynamical timescales. So that is a little bit about the stationary states. I'll move on to the evolution of these. So that these are put in as initial data into the code that's described by Oliver, and we initialize. So the states I just described are constructed purely as grid quantities in the code. So all the fields live on the grid. And to evolve these states in the particle and cell code, we need to initialize the particles. So this is done by introducing a grid of macro particle locations. So in the particle and cell scheme, right, these particles are not sort of supposed to be fundamental stars, say, but rather groups of stars that are somewhat co-moving. So some people call these macro particles. So we have a grid of these macro particles with some spacing drp, which is tied to the grid spacing drg, with some ratios as particles per cell in the r direction. So for the simulations that presenting today, this particles per cell is taken to be 1, so that the grid spacings agree with the particle spacings in each r direction and in the z direction. There are 3 different momentum directions to also deal with, and so for each of these we fix the number of particles, nv, and we try to place these somewhat intelligently. So rather than just throwing down NV ad hoc particles and hoping that they land somehow in the support of the distribution function in phase space, we place as NV particles at each spatial point, with their spread determined by sort of the bounds, which are specified by the distribution function. So this energy cutoff here at a given spatial location determines a maximum velocity that is, or momentum that is allowed for particles at that spatial location. And if you have a minimum particle angular momentum, then you have sort of a minimum momentum that's allowed in the v3 direction at that spatial location. So we place these particles intelligently in order to conserve resources. And we initialize these F tilde weights by, so there's this is rescaled, as Oliver said. So we have this distribution function. I'm missing an A in my formula from the amplitude that is obtained from the stationary states. We have the microscopic equation of state evaluated at the particle energy and angular momentum. And right, and these fields, so I'm denoting the little sub p on everything here as meaning the quantities which are interpolated to these particle positions. So the total number of particles in real space will of course be determined by the support of the matter. So large solutions with larger support are going to have more particles required to resolve them in physical space. So we evolve these with the stationary code. Some sort of typical parameters that we're using here are, so I have sort of two resolutions that I'm playing with. One is the high resolution, this grid, and hence the particle grid are also chosen to be 0.1. The maximum radius is 30, 25 in the Z direction, and this is slightly less because the distributions tend to be offset in the radial direction, whereas they're symmetric in the Z direction, and they also tend to oscillate in the radial direction. So I give myself a little bit more room to work with. 16 particles in each momentum direction at each spatial point, of course. And so for the stationary solutions that we're evolving, we end up with something like 10 to the 7 particles. So this code is designed to run on one node, shared memory architecture. This is about the limit of the memory capacity for the nodes that we're using at the Chalmers cluster. Does anyone have any questions at this point? So I go on to some results. So the first, or one of the things that we wanted to do, of course, is to exactly what Gerhard had brought up in the previous talk, was to investigate the stability of spherically symmetric states in this axisymmetric setting. So maybe I can first speak about what we find, and then the problems with handling spherically symmetric states. So with this investigation, we take this ansatz that so in our setting, there's very limited ways to obtain axisymmetry, but you have to, or sorry, there's only a certain combination of these parameters such that one obtains a spherically symmetric state. So one has to eliminate the dependence on the angular momentum, which in our case is the Z component of the angular momentum. So this means that I take L and L0 to be 0. And this K, we could choose to be something else here. I've chosen it to be 0 out of simplicity. So this leaves us with a distribution function, which is a Heaviside step function on the particle energy. So this is should be an isotropic steady state. And one can form a binding energy curve. So here I'm plotting the binding energy on the vertical axis versus this parameter E0 on the horizontal axis for a number of states. So stepping down, moving to higher redshift, more relativistic solutions here, and you pass a peak somewhere near E0 is 0.88 in orange. So I have evolved each of these states that is plotted with the code and find here in the plot on the right that each of the solutions up here near the peak is collapsing to a black hole. So this is in part signified by the central redshift is blowing up. So these states are evolved. So I guess these ones blow up fairly quickly, collapse to a black hole fairly quickly. This state E0 0.94 appears stable on a time scale of 300 m. So m, the mass of each of these solution is scaled, chosen to be 1. Right. So this simulation at least suggests that the spherically symmetric bodies become unstable to axisymmetric perturbations before the peak in the binding energy. So let me first move on to, maybe I can mention that, so there are certain issues with the axis in our equations. For example, in maybe I'm not dangerous to be too specific here, but there are certain powers of 1 over r that appear in the certain source terms. And this leads to nasty behavior if your particles intercept the axis. So we have implemented what I'm calling the axis exclusion tube, which is this thin tube around the axis, in which particles are forbidden to exist. So any particle that moves into this axis will be sort of shifted it would be reflected around the boundary of this axis exclusion tube, and its momentum will be switched. Just as if a sort of a mirroring particle was coming in from the other side of r equals 0. So that's sort of the problems that are associated with evolving these spherically symmetric states in our code in its present form. So that if I showed you a movie of these plots, there would be some undue noise around, close to the axis, and of course it would be nice to fix this, to investigate this more carefully. But okay, let me get back to this in a couple slides. So for this reason, we can look at the toroidal clusters, which do not intersect the axis. So I have a family of non-rotating, so chi is chosen to be 1/2, so that there are equal numbers of particles rotating in each direction, and some choice of these other parameters. But I have a lower bound on the particle angular momentum so that the particles are offset from the axis. And one has a binding energy curve for these solutions as well. So what I'm plotting in this plot is the binding energy in the vertical direction versus the central redshift in say the x direction here, and time in the other axis. So at time equals 0, one has the initial binding energy curve associated to this family of steady states. And then as time evolves, we can watch the solution in this binding energy central redshift parameter plane. So the binding energy is is an analytically conserved quantity, and numerically it is fairly well conserved because the mass is well conserved and the rest mass is also very well conserved. So you can't see it in this static picture that I'm showing, but each of these traces is largely constant in its initial binding energy. The central redshift, however, varies quite significantly. So for the states here near the peak of the curve, each collapses quite rapidly to a black hole. The central redshift goes to infinity. As you move away from the peak, you see states which evolve in, they exhibit some kind of oscillations before collapsing. This gray one, I needed the computational resources, so I stopped it after I could basically see what was going to happen. So this one does, I anticipate strongly that it will collapse shortly after. And at some point far down the binding energy curve, one has states which survive to 1000 M. And this is an arbitrarily chosen time at which I deem this, I don't claim that anything is stable in any absolute sense, but I numerically distinguish stability here by constant over 1000 M time window. This is also dictated by limited computational resources. So this is the status for non-rotating toroidal clusters. It also appears that the onset of instability occurs before the peak in the binding energy. Another way of looking at this is to look at the blow up of the maximum energy density, so the peak energy density. So this one basically sees the same thing. You get for these, the peak here occurs at this E0 0.85, which is in green, and solutions on both sides of the peak are blowing up quite rapidly. As we saw, slightly more non-relativistic states are exhibiting some oscillations before blowing up, and then far down we have states which are relatively constant. So to what extent can I believe these results? As Oliver said, we monitor the total mass as well as these residuals of the momentum constraints, which are not solved but just monitored. So in all of the simulations that I've just presented, the spherically symmetric ones and the axisymmetric ones, this mass is well conserved to within 1%, barring the point, barring the sort of region where it collapses to a black hole. So once the black hole starts forming, then this mass runs away much more rapidly. These normalized constraint residuals are also well conserved. They're something like 10 to the minus 2 for most of the evolution until the black hole starts to form. So by our methods of understanding the reasonableness of these solutions, the results that I just presented seem robust. There are a few other results on stability of axisymmetric clusters. So these were obtained by Abrahams et al. In 1994. This is working with Shapiro, continuation of the Shapiro and Tucholsky results. So they wrote a code to evolve axisymmetric solutions of the Einstein Vlasov system with rotation as well. They did initially study this stability of spherically symmetric solutions in their code. So they have an axisymmetric code, so they should be subject to all the same axisymmetric instabilities that we see in our code. The results that they present in their paper, which is notoriously sparse, is they exhibit, or they present two solutions, spherically symmetric solutions, one on either side of the binding energy curve, and they claim that their results are consistent with this binding energy maximum hypothesis. So they see the solution on the unstable side to collapse to a black hole in about 82 M for their solutions. And they do not say anything about the time scale on which their solution on the stable side persisted. But I do note that in their paper, the maximum time scale that they report evolving any solution is 140 M, whereas, let's see if I look at the stable side, which picture shows it best. So I went the spherically symmetric ones, right? So the peak is 88. The green one is on the stable side of the peak, and this collapses to a black hole, starting sometime after 100 M, it starts running away. So it's if I was to speculate, it's conceivable that Shapiro and Tucholsky simply did not evolve their stable side solution long enough to witness the collapse to a black hole. It's also conceivable that they were evolving a solution further away from the peak, and it was in fact stable. So without sort of reproducing their ansatz and their parameters identically, I can't say much more, and they do not present like a binding energy curve in their paper to compare with. There are
Ellery, just a comment. You have like 5 more minutes now.
I have 5 more minutes. Okay. Yeah. Thank you, Håkan. I thought it was going to be a short talk. What do I want to say? Oh yeah. So they also present results on stability of toroidal clusters, but they use a very different delta function type ansatz that we're presently in the progress of implementing, so we can confirm what they find. I do want to mention these results because perhaps some of the participants in the workshop have more experience and ability to comment on the similarity. So in the case of the fluid matter models, there is a foundational result in the astrophysics literature by Friedman, Ipser, and Sorkin that states this, for the fluid case, right, this concerned with this turning point principle, that the instability is associated with the maximum in the mass along this sequence of steady states. And this result of Sorkin et al. Says that along a sequence of steady states which has constant angular momentum, and this is for uniformly rotating bodies, that this turning point is a sufficient criterion for instability. So this is some statement in the literature that's based on a set of theorems by Sorkin, and maybe some of you can tell me or maybe someone's more familiar with this that knows the status of the level of rigor that's in this result. There have been follow-up numerical studies related to this. So Takami et al. In 2011 did some numerics for uniformly rotating bodies, and they find that in fact the instability sets in before the turning point. So it sets in at this so-called neutral stability line when the energy of a perturbation, they observe the energy of a perturbation vanishes, and that this difference between the neutral stability line and the turning point grows if you have more angular momentum. So similar results were also found numerically by Wei et al. In 2018 for differentially rotating bodies. So I'm wondering if what we're seeing is somewhat similar to this, this gap that appears is somewhat similar in the Einstein Vlasov setting applied to this binding energy instability criterion. So maybe I will skip this. So I have some results on the, what do I want to talk about next? 5 minutes. Okay, so I'm almost out of time. So I will skip this effect of rotation on the stability and look at perturbations. So I have also, we started looking at explicitly perturbed steady states. One question is what are the end states, as sort of Oliver hinted, what are the end states of these subcritical perturbations? And this is unknown. So according to this proposition in our first paper, that if the binding energy is positive, then the support must, the solution should not fully disperse, but remain bounded. So in part, to explore this kind of behavior, I've taken unstable steady states and introduced sub-perturbations of these states. So the general behavior, so this is motivated, of course, because in the Einstein Vlasov system, the critical states are supposed to be, or thought to be, unstable steady states. So these should be sort of subcritical evolutions in a critical collapse setting, potentially. So general behavior is what we observe is some sort of oscillations. The oscillations are quite pronounced for this extreme. So what I'm doing here is whacking the solution by cutting down the amplitude by some fraction, 0.8 in blue. That's quite extreme. I'm not sure you would call that a perturbation, but you do see oscillatory behavior, and this oscillatory behavior becomes less pronounced the smaller this perturbative amplitude. So I'm not. This needs more work and more digestion to resolve. I maybe want to close by showing a movie, because in Olivier's talk, was it yesterday? I was motivated, or 2 days ago, I was motivated to look at the dynamics in the phase space distribution. So Oliver already showed these oscillations in the energy density, and I can't, the movies I have are going to be very similar, but this dynamics in the phase space distribution is somewhat interesting. So I am presenting this for perturbing amplitude 0.95. So it's this green trace right here, sort of expands and then eventually collapses to a black hole. Let's see if you're actually able to see this movie. So can you see the initial movie on my screen at least. Yeah. So I play. So I don't know how smooth this is over Zoom, but you see it, some sort of mixing in this phase space. What I'm plotting here is the radial direction in the horizontal axis versus the radial direction of the particle angular momentum. So I play it again. You start out, you see this discretized particle distribution, which then evolves into this corresponding to the perturbed stationary state, and it evolves into this sort of this other state before collapsing to a black hole. So it's not the ideal case to look for like phase space mixing or settling down into a different stationary state, but it's the evolutions that I had to play with between Olivier's talk and my talk. So I think with that, I finish. Thank you.
Okay, many thanks, Ellery. It's nice talk. So, are there questions? It's late in European time. So, any questions?
Can you maybe quickly comment this thing that you skipped? So rotation and stability. Can you just maybe just briefly say? Does it make it more or less stable?
Yeah, I think there are two ways to introduce rotation in the models that I'm looking at. So one is to introduce it via this counter-rotating fraction. So everything that I had presented above had equal numbers of particles in both orientations. So one thing we do is to unbalance this, introduce unbalance into this. And I do not observe any stabilizing effect from introducing this unbalance. If anything, actually, it increases the the point of instability. Maybe I should enter it this way. So if you have a rotating solution, so chi is a quarter, say, then the peak in the binding energy curve is pushed to higher redshift. But the instability that I see sets in at about the same redshift for both the rotating and the non-rotating. So the instability is further from the peak in the binding energy curve in the case of a rotating solution. That's sort of my quick and dirty summary of what I found. Mm-hmm. The other thing one can do is to increase the minimum particle angular momentum, but I don't have sufficient data to say anything on that yet.
Mm. Okay, thanks.
So also Simona Calogeri wanted to ask a question. Please, Simona.
Yes, sorry that you cannot see me, I don't have a camera. So is it the case that your axisymmetric solution, they all have a shape of a torus, or the interior of a torus?
Yeah, they don't all. So this definitely depends on the choice of parameters that one makes. So if you choose this L0 parameter to be non-zero, to be positive, then they will all have a toroidal cross sections. But if you choose this to be zero, then in principle particles are allowed to be at the axis, and then you can control how they the distribution, how it's shaped sort of away from the axis by this little L exponent.
But in any case, what my point was here was make is, shouldn't also the stability depend somehow on the shape of these galaxies? Because we see only a very limited type of shapes of galaxies.
Right.
In the universe, we never see an egg-shaped galaxy, so which is actually symmetric. So is there any reason for that?
That's a good question. It very well could be that this family of states I'm looking at is has certain stability properties, and a different state has different stability properties. I can't say anything based on what our numerical experiments are limited so far, and I don't know anything from an analytical standpoint. I will just comment that they do observe some toroidal galaxies in nature, but I can't say anything else. Yeah.
Thank you.
Okay, so then also Sebastian Günther has a question, please.
Hey, Sebastian. I can't hear you yet.
Can you hear me now?
Yeah, there we go.
Okay. Well, I have a lot of questions actually, but I will focus on one of the most important ones. So you look at those spherical symmetric steady states with k equals 0. The first one you showed, I think.
Yeah.
What kind of amplitudes did you use to perturb this steady state?
This is actually unperturbed. So this is just the only perturbation is coming from the numerical discretization.
Okay. And of course, in the spherical symmetric case, k equals 0 is quite problematic, actually. Have you tried other values for k, and did a similar thing appear? Because we even excluded in our paper the case k equals 0 because the initialization is very, very difficult, even if we use millions of particles in the spherical symmetric case.
Yeah, this is a great point, and unfortunately, something I thought about only after I had run these evolutions. So I am currently running simulations with larger k, but this is not finished yet, so I can't present the results. But your question is certainly interesting, valid, and something we're looking into.
Okay, thank you.